Hello my friend, today another boss fight. We have to recreate the printf function. Of course, I'm not gonna recreate the full printf function, otherwise we're gonna stay here all day long and that is not the point. We are rather going to understand the overall principles related to variadic functions and the printf, okay? So basically we have to write a function named myPrintf that will mimic the real printf. We can use the malloc and the free, so the functions coming from the standard library to manage memory, right, in the heap. We can of course use the write system call, and then we can use these va start, va arc, va copy, and va end. These are macros coming from the standard argument header file. I already made a video about these ideas, you can check. And today we are just gonna very briefly refresh our memory about this concept. But if you don't understand what is going on at all, I suggest you to watch my previous video. So the prototype is gonna be specular to the real printf. We have an int myPrintf, const char star, and 3 dots. These 3 dots are an ellipsis, as it is called. And these 3 dots imply that the function can take variable number of arguments. Indeed, the printf function is a variadic function. You know very well that you can plug inside this function as many arguments as you want. How does it work? How can the printf behave such differently from all the other functions? As you know very well, all the functions need to have a very tight description, a very tight API, a very tight prototype, right? So you have all the times to explain to the compiler, hey, this is the function that has this specific name, is returning this specific data type, and is taking these specific inputs. The compiler always needs to know this stuff, right? This is not the case for the printf and all the variadic functions in general. So today we're going to understand super well what is going on. Of course, my printf is going to be just a little sample. Maybe it is going to be part 1 of the printf, quote unquote part 1. We're going to only explore the overall ideas. We're going to create my printf that is able to print a char, a string, a decimal, and an hexadecimal digit, okay? Otherwise, this is going to be too long. And once you grasp the overall principles, you can go by yourself very simply. So quick refresh to a variadic function. What is a variadic function? How does it work? I strongly believe that practice is far better than theory, so we're gonna check a real example. Here, my friend, as you can see, I have a function that is called average that is taking an integer and 3 dots, so an ellipsis, namely a variadic number of inputs. So the function average is able to take whatever number of inputs and giving me back the average, right, of all these inputs. As you can see here, I have VA list with the name AP, VA start, VA arc, and VA end. So I'm gonna go very fast because I already explained all of this in the previous video that I told you before, so maybe you now know everything super well. Long story short, I have to use in my average function the first value, the first int, as you can see here, as how many arguments are gonna be there, right? I have 5, so I'm gonna have 5 arguments. This is a crucial value, this 5, because otherwise the function average at this level doesn't really know how many arguments are gonna be there. So this is important. The first argument is gonna declare how many arguments are gonna be there, and the following arguments are the actual variadic arguments. So this function is able to take all of these arguments and tell me back what is the average of all of them. Okay, this is cool, but what happens in the printf function? In the printf function, I have something like that, right? Printf, then I have hello as today is %d, okay? And here I have all my arguments, right, on the right. A literal string, for example, John, and here I have a number, for example, a date, let's say 27. Where I can find the number of arguments inside the first argument of this variadic function, because the prototype of the printf function is this one, int printf. Then I have my format str, okay? And then I have the ellipsis, okay? So here the real prototype, of course, is const char star. So here I don't have a specific number like in my average function. You see here, I say, okay, this is a variadic function. The first one is gonna say how many arguments are going to be there, and these ones are the actual arguments. In my printf, on the contrary, I have other elements that are going to signal how many arguments are going to be there. These elements, of course, are the percent sign, okay? Every time I stumble upon in my string in a percent sign, I know that, hey, there's going to be an argument there, right? If I iterate inside my string, HELLO space, then I stumble upon the percent sign, I'm going to say, hey, oh, wait, here is going to be an argument. So here I can very easily say that I have 1 and 2 arguments. Indeed, these are the arguments of my printf. So I don't explicitly need a number, for example, like in my average. I'm just going to derive very easily from the amount of percent sign how many arguments are going to be there in my printf function. Easy, right? I'm going to just give you a visual understanding, even though I explained in the previous video, but just to have a little refresh. As we say, repetition is the mother of learning. It's very, very important to repeat all the time the same things. So I have my object, VA list, that is called AP. AP stands for argument pointer. Indeed, this is a pointer to the array of arguments or vector of arguments, VA vector arguments list. So the amount of arguments, even though I saw on Stack Overflow that VA stands for variable, but that's not the point, even though if it is variable or if it is vector, that's the same. The important thing is the principle, is the idea. So basically you have a pointer to a series of arguments, as you can see from the image. Then I say VA start. This is gonna start. This is gonna move the pointer. It is gonna move the needle toward the first real argument, because you understand that in my average, the first 5 is just a flag value. It's gonna indicate how many arguments are gonna be there. I don't want to use that to perform the actual algorithm, to perform the actual average. So vstart is gonna move the needle, is gonna move the pointer just 1 position after the first flag argument. So now AP after VA start is at the right spot, is at the beginning of the actual arguments. Cool. Now I can do a loop, right? I can do a simple for loop. I say I equals 0, I minus number plus I, and I loop inside the argument. To fetch every argument, I need this macro, which is VA arg. Basically, every time I call VA arg, I'm gonna fetch the next argument. I have to give to VA arg the pointer, which is argument pointer AP, and the specific data type that I want to retrieve. So this VA arg knows exactly what is the amount of bytes that has to fetch from memory, okay? It knows very well, it knows exactly how to perform its fetching function. So every time I'm gonna fetch one element, in this case I have all integers, so I'm gonna fetch every time an integer. Then at the end I have VA end, that is not really important, but basically it's cleaning up all the mess, all the data generated by VA start, VA arg, and VA list. It's like if you want quote unquote a free of a memory allocated in the heap, okay? So it's a cleanup function. So I think it's pretty easy to understand, right? What is going on with the image. It's very easy. Now there are some subtleties. If you want to see much more details, just watch my previous video. I go a little deeper, even though you don't need that. All right, we are ready to start with our printf. I do vim printf.c. Okay, enter. I want to make just a single file. I'm not gonna make a project composed of many files that I need to compile and link together. I want to make this video super simple initially, just to grasp how to handle a periodic function like the printf. I repeat to you, maybe I'm gonna do a part 2 where we are gonna create the actual printf, which is kind of longish and not very easy. So we're gonna include standard input out. I want to use the printf just to double check my results coming from my printf. Then of course the unistd to use the right function, include the standard library to use malloc and free, and that's it. So we're gonna start from my main. So int main, and here I have, for example, my printf, and I have %s, for example, hello %s \n, and my printf has to be able to print the string, right? So here I have, for example, string literal John. Of course, I want to capture the amount of chars that have been written. So I do a variable that I call count, and in count I put the result of my printf. Then I'm gonna just print it. So printf, I'm gonna use the real one, or I can use mine as well. I can do my printf, and I'm gonna put inside the chars read are %d, okay, \n. And here I just put count. So this is the first argument. All right, let's start like that. Then we're gonna do all the other tests. So we're gonna implement our printf. So as usual, an int. This is gonna be the number of chars written in the standard output. Then the name, so my printf. And then inputs are gonna be const char star that I can call, for example, format. This is indeed a format string. That's why the printf has this f at the bottom. And the second input, of course, is going to be an ellipsis, these 3 dots. These are going to say to the compiler, hey, I don't know how many arguments are going to be there, because this is a periodic function. Cool. Now we have to do our housekeeping, right? We have to use the macros coming from the standard argument header file. So of course I have to include the standard argument. And what do I have to do? I have to declare an object that contains all the necessary data to loop inside all the variable arguments coming as an input. So I need to create this object, which is VA list, right? That is a standard called AP. AP, that stands for argument pointer, okay? So I have a pointer that points toward the first argument, which is the string format. Okay, of course, here I don't have the star like normal pointers. I already explained this stuff in the previous video, but this is low-level stuff. You don't really need to understand so deeply everything. So you create this pointer, VA list AP. Now remember from my function average, now I need to start, right, to init my argument pointer. Basically, I have to skip the string format and go to the real first argument, right? So I need to use this macro, VA start. So I'm going to do VA start as an input argument pointer, and then param stands for the first parameter, which is format in my case, the string. Okay. Now, thanks to this VA start, AP is pointing to the real first argument, that in my case is John, right, in the first example. Now, my printf has to return the amount of chars written, so I'm going to do integer, I don't know, count. And then I do count equal 0. Of course, every time I have to initialize my variable, otherwise they're going to be garbage values. Cool. And then what do I do, my friend? Well, you recall that I told you that to check for all the arguments, I just have to loop inside my string. And when I stumble upon a %sign, I have to say, hey, here, there's going to be an argument. I know that. It is like, it is a flag, basically, that is telling me, hey, here there is an argument. So I loop inside my string while what? While at string, so at format, is different from 0. Here I can skip. Different from 0 is redundant because I can use directly the \0 as a boolean value, but I will write for making the code more readable. Different from 0 or \0, that's the same, like that. Okay. So until I have a string, until I've not exhausted all the string, what do I do? Well, I have to check for %signs, right? For these specific flags, which are specific to the format string. So what do? I say if the char pointed by at format is equal to %sign, here we can create a special function ad hoc that we're going to do. Yes, we're going to say print format. As an input, it takes. I want the specific char, right? I want the C, the S, the X, or the D, right? The flags that are just after the %sign. So I say at ++ format. Pay attention here, the ++ has more precedence than the star sign because they are both unary. But association, when we have unary operators, is from right to left. I already made a video about that if you want to check it out. But here, just to make it simple, without all this madness of operators precedence, you can do like that. You just use the round braces, and that's it. So it's fairly clear what is going to happen. I'm just gonna increase the pointer format, and then I'm gonna dereference it. So I'm gonna get the char. What char am I gonna get? Here at this level, at format equal %, I'm here, right? I'm exactly here. So I have my pointer that is pointing exactly to this. Then when I increase ++ format, my pointer is moving one position. So the pointer now is pointing here to the S. And then I simply dereference this pointer. So I get this S here, you see? So here I have exactly the conversion specifier, the char that is saying, hey, I want a string here. And then as a second input, I give AP. So I give a pointer to all the arguments. Print format is going to handle all the possible cases. For example, if I have a string, a char, an hexadecimal, and so forth. Okay, we're done. Of course, we have to implement print format. So if at format is equal to %, you have this special function that is handling all the possible cases. Of course, I have to save all the chars that are written. So I'm going to do count + print format. So print format is going to return me back the amount of chars that have been written. On the contrary, else, well, it means that you have a simple char coming from a string. So you just print that char, very simply. So to print a char, we use the write system call in the standard output, so 1. Here, the write wants a buffer, so a pointer. I give directly the format, which is the pointer to the string, and only 1 byte. Okay, easy peasy. Then the write system call function is returning me back the amount of bytes, the amount of chars that has written, right? If you do man to write, you can see at the return value that upon successful completion, the number of bytes which were written is returned. Okay, so here I have 1 that is returning me back, and I want to capture it because at the end I want to return it. So I do count + write, and that's it. At the bottom, I have to increase format. So I have pointer arithmetic directly to the pointer itself. I'm not going to use an iterator like I or something. I just increase the pointer itself. And we are basically done, I think. At the bottom, we have just to return count, which is the number of bytes, the number of chars that have been written. So this is the blueprint of my my printf. Here, of course, at the bottom, I just do va end. So I have my garbage collection, quote unquote, function. And now we are able to write my print format. So I increase a little bit. Okay, my print format, the function that I've written here, is returning me back as well the amount of bytes written, print format, and as an input is taking char, that is the format specifier of the printf function. So I call it specifier. And as a second input, we have our special object, which is a vector argument list that I call as well AP, argument pointer. Cool. Now, as always, I'm going to declare a counter. So count, and as always, count equals 0. Ad nauseum, I'm going to repeat. And then very simply, I have to check, is the specifier this? Is the specifier this? Is the specifier this? In that case, you do that. I say if specifier is equal to C, that stands for char. Now I need also the braces, of course. What do? You do something. Now I'm going to create a function that I call, for example, print char. Print char that is taking what? I need the argument coming from the object va list. So for this, we have our special macro, which is va arg. Fetch the next arg. Okay, so I can do va arg. Va arg wants the pointer, so AP, argument pointer, and then va arg wants the specific type that we want to fetch, for example, char. Now, here, my friend, there is a little trap. That now I will explain. I hope you are familiar with the concept of type promotion. Basically, type promotion is an automatic conversion of data types from lower ranking to higher ranking data types. For example, here I have a sum between an integer and a float. And here what happens, I have a promotion, okay, which happens implicitly because I don't have any loss of data, and integer is promoted to a float. And that's what happens underneath the hood. When I say higher ranking, I'm not only implying that the data type is bigger in terms of bigger bytes, because for example, an integer and a float are both typically 4 bytes, but float can represent a much bigger range of values, right? Because in the way float numbers are stocked inside the RAM. So higher ranking data type is not the same as bigger data type. Pay attention to that. So here, I think the concept is fairly simple. You can search by yourself what is this type promotion in C. Of course, you can do also this conversion explicitly thanks to typecasting, right? Now, what's the point with this promotion? Well, what happens when we have arguments which are passed to a variety function is that we have a conversion. Let's read together this little extract coming from the Kernighan and Ritchie book, The C Programming Language. Type conversion also takes place when arguments are passed to functions. In the absence of a function prototype, char and short become int and float becomes double. Of course, this is true when we don't have a prototype, because the prototype is strictly telling, okay, the arguments that are coming are specifically these ones, so I can receive a short or an integer. So promotion stays when we have an absence of a prototype, like in my variadic function. Because in my printf, I don't know which are the data type of the arguments that are gonna come. So what happens is that we have a promotion. Since the prototype doesn't specify type for optional arguments, in a call to a variadic function, the default arguments promotion are performed on the optional argument values. This means that objects of type char or short are promoted to either int or unsigned int, and floats are promoted to double. So if the caller passes a char as an optional argument, it is promoted to an int, and the function can access it with va-arg ap int, like in our specific case. So you know perfectly well the data types, right? We have basically a family, that is the integer data types and the real type. The way in which data is stocked in memory is qualitatively different, right? When we have real data type, we have 8 bits, which are for the exponent. So these make the encoding really, really different. If you watch 42.0 and 42, the binary configuration is very, very different. Anyway, this is low-level stuff. The thing you have to understand is that a char, at the end of the day, is just 1 byte integer, right? It is a 1 byte integer. An integer, of course, is a 4 byte integer, and a long is usually an 8 byte element. So when I pass a char to a variadic function, the variadic function is not going to take a char, right? It's not going to take a short, but it is going to take an integer, because I have this promotion that is happening underneath the hood. As well as if I pass a float, I'm going to get, indeed, a double. I can do that because a char and a short are just smaller integers, okay? Easy. So here I found online some other informations you can screen, you can check it out, but this is low-level stuff. You don't really need to understand. That's why we programmers work at a higher level of abstraction. This is stuff for electrical engineers, basically. So here, our mistake, practically speaking, is that here I don't have to use a char, but I have to use an integer, right? I'm gonna fetch the next integer. A char is 1 byte integer. Cool. Then, of course, I have to save the char that has written. Count is equal to print char. Okay. So my print char is gonna give me back the chars written. Okay, let's do the other case. Else if specifier is equal to s, so a string. I do here I forget the plus equal. Print string, print str, and of course I'm gonna fetch this time from the pointer a char star. Char star is a pointer, so of course it's not gonna be promoted. Then I have else if specifier is equal to d for digit, count plus equal print va-arg ap integer, right? Semicolon. Else if, you see, I just need to take all the cases possible, right? Specifier is equal to x, so we're gonna do an hexadecimal. And now I can be smart. Here, indeed, I forgot to print digit. I can do, I can use print digit to print also the hexadecimal. So I can use the same function for both. Okay, so, okay, I think I can do that. And we are gonna spend a little time on that later, so you will see what I'm doing. Okay, print digit again, and I do var ap, and here I write unsigned int. You will understand later this point. And then of course I'm gonna add the base, otherwise my print digit doesn't know how to handle that value. So here I have base 10, and here I have base 16. All right, let's finish this. Now I have all my specific cases, right? My printf is really little. So I have a char, string, digit, and hexadecimal. Let's make a case in which I have a strange conversion specifier. So I do else. Else you just write the specifier, even though this is not what happens with the printf. I think you have undefined behavior when you have a strange specifier in the standard output. The specifier, so I need to give the address of specifier and 1. Okay, so I have here all my cases for my little printf, and then of course at the bottom I do return count. I think we are okay. So now I just need to implement these functions, which are rather simple, right? Let's start from the first one. So print char, return the number of bytes. Print char as an input, I take an integer, right? I take an integer int c. I repeat to you that a char is just a 1-byte integer. So I will exploit the write function that is returning the amount of bytes written. So I do return, and then I call the write standard output address of c 1. That's it. So this is my print char function. Very simple, right? Then I'm gonna do my print str. So int print str. As an input this time I take a pointer, right, to a char. Char star str. So I need a counter. So int count. So counter count is equal to 0 as always. And then I say while at str as usual is different from 0. I'm just gonna delete this because you know it's redundant. Ask open. I want to write this, so I'm gonna use my print char at str. I need to convert to an integer, and I'm gonna increase by 1 counter, and of course I'm gonna increase str. Of course this is poorly written. As you can see, I have to make all these increase. I can use directly str plus count, but I think this is more readable and I want to make it simple. So I do return count. So every time until I have a char, here let's make even more simple like that, different from \0, which is 0. So until the char pointed by str is different from the last sentinel one, you just print that specific char, you increase count by 1, which is the number of bytes, and you increase str, which is the pointer, right, to the char. Then at the end you just return count. So we are done with the print str function. Now with the difficult one. This one I'm gonna do a little difficult, my friend, allegedly. So I need a function that is able to take a value and spit me back in a specific base. Here with hexadecimal I use unsigned. Now you are gonna see why. In the real printf, when I want to write printf %x new line, for example 42 or minus 42, and here if I do the same with a digit, so I do 42 minus 42, let's check what happens. You see that what I get is an hexadecimal representation that doesn't have a minus. Basically this is the binary configuration of minus 42. So to make it more clear, let's do the number -1 and -1, of course. So you know that -1 has all the bits turned on. So we run the code again, and as you can see, my hexadecimal representation has FF, 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 FF. One hexadecimal letter represents 4 bits. So here I have 1 byte, 2 bytes, 3 bytes, 4 bytes, indeed an integer. Basically, I have all the bits which are turned on. So when I want the hexadecimal representation of a negative number, I get the binary. I get the binary representation. I don't get the -1 like in decimal. So basically for hexadecimals, the printf is taking only unsigned values. You understand what I'm saying? I just don't get a -1, or like in this case, if I have -10, I would expect like a -a in hexadecimal, right? But as you understand now, this is not what happens. I get the binary representation without any minus sign. Cool. So now you understand why here I use an unsigned int, because that's how the function works. So this is the first riddle. Now you understand why I use print digit for both. How does it work? Well, of course, I have an integer, the number of bytes that are being written, and then I have print digit. So print digit is taking a value, but here I have to be smart, because if I get a negative value and I want to implement this with recursion, if I change the sign, I will get problems with the overflow. So what am I gonna do? I'm gonna cast the value that I take here to a long. So I do long here, and I do as well a long here. So this is an explicit cast, right? I'm gonna convert two integers, one signed and the other unsigned, to a long. So you see what happens here, my friend. I have var that is fetching an integer, a signed integer, and then I have an explicit typecast to a long. So the print digit is gonna receive back a long, as well as with the hexadecimal. This is cool for two reasons. The first one is that I can trick very easily the overflow when I have a minus sign. And the other thing is that the print digit doesn't really know if the input is coming from the decimal digit or from the hexadecimal one. So the print digit can be used by both, and the print digit doesn't know anything. For the function, it's totally the same. Okay, so we do long mbr, or only n, okay? And then I have int, which is the base, okay? Which is the base of the number, hexadecimal 16, decimal base 10. I want to do something that maybe is not so simple to understand, but let's try. First of all, I need a counter, because I want to stock all the bytes written. And then I'm gonna do recursion, which is not super simple. First case base, when a number is negative. So I'm gonna do if n is minor than 0. Ask open. What do we do in this case base? Well, in this case base, I want to write the minus. Of course, this minus 0 is only for the decimal in this case, because the hexadecimal is going to be fetched only as an unsigned. So the hexadecimal is out of the game. This is only a thing for the decimal value. And if the decimal value is minor than 0, what do we do? Well, of course, we have to write a minus. So we're going to do that. Print digit. I'm gonna use my function print char, or I'm gonna use the write. That's the same. Write in the standard output a minus, so a string literal minus, and one byte. Okay, so if the number is negative, you're just gonna write immediately a minus, and then you have to do something tricky. You have to recall again the print digit function. No, print digit. As an input, you give the number, but this time you have to give it positive. So you're gonna reverse. To reverse a number, you just do minus n, or n per minus 1 is the same. And then, of course, the base. Okay, so you have a recursive call. That's not the full story, because at the end of the day, I want to return the number of char that have been printed. So I need to do return print digit. So I'm going to return all the digits that are printed, but not only that, I need also to add 1. I'm trying to explain you now. +1. Why this +1? Well, because here I have one char that has been written at this level. You see? So I'm going to say here, okay, in this specific case base, if the number is minor than 0, you just immediately write a minus, and then you call again yourself. You do a recursion, but this time with a positive value. So you're going to get rid of the minus. And all the chars that are going to be returned, all the chars that are going to be printed by all the recursion that is going on, you add 1, because it's the minus that I've written, specific base case. Okay, this is kind of a mouthful, but let's keep going on. Later we're going to watch on C-tutor so we can understand. Then, given that we are dealing with the base and with the write function, I need a series of symbols. I need a series of symbols that I call char star symbols. And here I do symbols are equal to a string, which is 0, 1, 2, 3, and all the symbols available, right? All the symbols available to write an hexadecimal in lowercase. but these are also the symbols to write a normal number. So it's pretty useful. Other case base. Which can be the other case base, my friend? Well, other case base is else if the number is minor than what? Than base. For example, if I have a number which is, I don't know, in base 10, I have the number 7, I'm gonna write it directly, right? I'm gonna write, because it's less than the base. I don't have to do any kind of arithmetic. So if the number is minor than the base, what do? You want to write the specific number. I can do in this fashion. I'm gonna use my print char function. Okay, I'm gonna use my print char function here, and I do return, because of course I want to return the byte written. Print char, and the function is taking an integer. Of course, a char is just an integer, so I do symbols. What is the thing I want to write? Well, let's pretend I have the number 7 in the base 10. I want to write the symbol 7. Where I can find that? Well, I can find here in position, what? Position 7. As simple as that. So symbols in position n, right? Do you understand this point? If I have a number that is in base 16, the number 11, for example, or the number 10, in base 16, n is minor than the base, of course, so I'm gonna choose symbols in position 10. And in position 10, of course, I have a, which is exactly the symbol to represent that specific value. That's it for this case base, okay? So here, the first one, not totally appropriate to call it a case base, because here I call the recursion as well. This is a tricky recursion, I understand, but we need to do something difficult at times to improve. So the last one is gonna be else. Now, in this case, I have a number which is major than 0, right, of course, and a number which is major than the base itself. So I have, for example, in base 10, here I can have the number 42. What do I do in this case? So I have to stock in a variable, which is this one, the variable count. Count is equal to all the chars that are printed in the recursive calls. So I do count, print digit. As an input, I give the value divided by the base, okay? So if I have 42 here, I do a recursive call. I say 42 divided by base 4. 4 is gonna go again inside the function, and it's gonna stumble upon the base case here, right? In that case, it's gonna return here. So it's gonna return 1, the function, okay? And of course the base. So it's gonna stock the return value from here inside count, and of course it's gonna print the 4. Then what do? I say return count plus, now I have to write the char which is at the bottom of this specific recursive call, and I can do like that, very strangely enough. I can do print digit again, and as an input I do, and this time modulo base. So I'm gonna take the last digit inside that this specific recursive call, and then of course base. All right, my friend. I think we are okay, my friend, with this crazy recursion. I think I managed to make something which is totally alien, totally not explainable in simple words. First of all, let's check if it works, because maybe it's not going to work. So here, what do? We're gonna just comment out this, and we're gonna do my printf %x new line, and of course I'm gonna do 42 initially. I put in count equal my printf, and then I say my printf the chars written are %d. Okay, so I'm gonna use also that count. All right, basically I'm calling my function to write in hexadecimal 42. Let's try out. I think everything is correct, but it is impossible. There's always some bug which is lurking somewhere. Okay, let's try to launch and let's check it out. So gcc printf.c, it compiles. Wow. So a.out, the charts reader on a 3. Why is that? Oh yeah, because I have the new line also. So it seems like it's working. Let's try to have the real one also. So printf with the same input here. So I'm gonna do count equal printf, and then again I'm gonna call my function to print the digit, but this time I'm gonna call the real one. printf. Okay, let's try to launch again. Compile and launch. All right, the outputs are specular. Here you do -1 that we saw previously as written in that strange way. Compile and launch. As you can see, they are the same. The charts written are the same. So it seems like my recursion is working properly. Let's try to do int min, int32 min, int 32 min, compile and launch. All right, they are the same. Perfect. And the bottom we can try with the 0, which is always something. We do 0, 0. The chart written are 2. Perfect. All right, it seems that everything is working correctly, allegedly. Let's try only with digits now. Digit int32 min, int32 min. Okay, let's compile and launch. Compile and launch. What happened? Oh yeah, of course I have to change this to digit. Compile and launch. All right, I think we are we are done, my friend. I think it works, right? So now let's do just a big one string to see if everything works correctly. Okay, I'm gonna do my printf, the hello %s. Today is %d, in x %x char. See, new line. Okay, as an input I give a string literal, John, comma, 27, comma, so decimal 27, and char z. Let's try to check if it works. Compile and launch. What happened? Segmentation fault. Segmentation fault. I forgot here something. I forgot the comma. Probably that was the mistake. I hope. Hello John. Today is 27 in x1b. Is it? 16 plus 11. 27. Yeah. Char z. All right. My friend, it seems like it's working everything perfectly. Maybe there is some bug here and there. I really appreciate it if you find it out and you tell me. But that's not important. You understand the overall point of this printf, how it works, how we can handle many arguments, right? This is the blueprint, right, of the printf. You create this VA list, vector argument or variable argument, call as you want, that contains all the arguments. Then you just start the machine. You start the process. You just shift to the first real argument, which is in my case John here, for example. This is when you do VA start. Now we are pointing here. We're pointing toward John, right? And then when I say VA arg, you fetch John, right? You fetch John. Then you go down. You do VA arg. So you're gonna fetch this 27 and so forth. I think you understand super well what is going on. Maybe the most difficult part is this recursion, right? You tell me, is this difficult? Do you find it like impossible to understand, or it's only my opinion? Because I'm a suck with recursion. I can write something like that because I'm street smart about that. I understood. I have my mental model to get what is recursion, and now it's like gut feeling recursion. I made a video about these ideas, so you can check it out maybe, so you can develop your gut feeling about recursion. The point is that recursion is really tricky to explain. At a certain point, you have to understand by yourself. I only managed to tame this subject only through practice and through developing a certain way of seeing the problem, which is subjective, right? One really cool thing that you can do that I always suggest is to come here to C Tutor just to watch what is going on. As you can see, I have the number 255. I want to write in base 2. So I have my number 255 with all the symbols. We go on. Every time, what happens? I go at the last recursive call, right? Because the number is bigger than the base and it is not minor than 0. So every time I start again, until basically the end, until basically I don't stumble upon a number which is minor than the base itself. In this case, I have base 2, so I have to arrive to the number which is equal to 1. Then I'm gonna go back, okay? So I'm gonna go back, I write the 1, and then we go back, so I'm here. I'm gonna do return count, which now is 1, plus print digit So I do another recursive call and so forth. So bro, I suggest you to come by yourself and just check very visually what is going on. Why I do need this array, these strings, this string of char of symbols to exploit, and how this function really works. I think that this is the most difficult part of the printf, because I'm an idiot. You can also do it iteratively, much more easily, but sometimes it's cool also to try something different. All right, I think that's it for this printf. Hopefully there's gonna be a part 2 where we're gonna do much more stuff, because printf is much more than this. You know, you just tasted a little bit the printf. So maybe let me know in the comment if you're interested to see all the deal. Thank you for watching. Enjoy, my friend.